Okay,
Okay,
please,
right.
please, Sachin, take care of that. Okay, let me introduce, say Professor Manoj Datta. So the another elegant, say the speaker in line, and he's my colleague, say at IIT Delhi. So the Professor Manoj Datta is currently the professor in the Civil Engineering Department at IIT Delhi, where he has been teaching, conducting research since long, 1980. So for the past for 40 years or so, so he's been doing extremely tremendous work. His area of research are geotechnical and geoenvironmental engineering, landfill engineering, soil mechanics, foundation engineering, ground engineering, and earth dams. So he has edited 3 books in the areas of landfills, solid waste management, and ash ponds. He has co-authored a test book for undergraduate students titled Geotechnical Engineering with Professor S.K. Gulati. It's a very popular test book. So the most of the undergraduate students also they follow this. He has published more than 160 papers in journals and conferences. Professor Datta has been consultant to over 150 projects in the areas of geotechnical and geoenvironmental engineering. He has been involved in planning, design, construction, and remediation of over 2 dozen waste disposal sites in India. He has been associated with the Central Pollution Control Board, Ministry of Environment and Forests, as well as the Ministry of Urban Development in framing of guidelines and design manuals for the municipal solid waste landfills and hazardous waste landfills. Professor Datta has received 5 Best Paper Awards of the Indian Geotechnical Society. He was awarded the IGS Delhi Chapter Leadership Award in 2008 and delivered IGS annual lecture during the IGC 2011 at Kochi. He was awarded IGS Delhi Chapter's Lifetime Achievement Award in 2017, as well as the Teaching Excellence Award by IIT Delhi in 2018.
Okay, good morning to everybody. Is my screen visible?
Yeah, it is visible.
Thank you. So I have 25 minutes or 30 minutes, Professor Rao? Okay. I'm going to speak about geoenvironmental considerations for bulk reuse of municipal solid waste residues. And the background to this this presentation is, if you can see, there are these 3 mounds in Delhi, which are about 60 to 65 meters high. They are filled with 6, 8, and 14 million tons of waste. And when you mine the waste from these mounds, you get soil-like material. And can we reuse this soil-like material in geotechnical applications? That's our aim. Also, in the recent years, we have set up 3 waste-to-energy plants in Delhi. And these plants are receiving about 2,000 tons of waste, and they are producing 600 odd tons of ash. So about 2,000 tons of ash is being produced of the municipal solid waste by these plants. So once again, the thing is, since the majority product is bottom ash, can we reuse bottom ash in geotechnical applications? The philosophy is that if you have a waste dump and if you can excavate and screen and process the waste, you can recover combustibles, building materials, and rejects. So the focus on geotechnical engineering is, can I use the soil-like material for the purpose of earth filling? So bulk reuse of soil-like material as well as the waste-to-energy ash, which is now coming out in huge quantities, is the focus of this paper. First, we will look at soil-like materials, and what we will get from here is that if you look at literature, most of the soil-like materials which have been excavated and segregated have been used at the landfill site itself for the purpose of a daily cover or the final cover of the landfill. So what we did was we collected waste from all the three dumps and screened it and looked at their visual composition. So bulk of the material is soil-like, some of it was gravel-like, and other minor components. So if you see, if I look at the material passing 20 mm, 72 to 77% material is soil-like or fine gravel. About 18% is the C&D waste, which is greater than 20 mm, and the other things, combustibles and others, are in smaller quantity. So, and if I do a grain size distribution, proper grain size distribution, that means I am doing washing to actually determine the amount of fines. Then what we see is that, what we see is that 45 to 50% is in the sand size range, and 20% and above are in the silt plus clay size range. And if I look at the major minerals, we are not trying to find out all the minerals because the soil-like material is quite heterogeneous. If I look at the major minerals, what is standing out from the soil-like material is quartz, calcite, and feldspar. And if I do the XRF studies, then again, this is reinforced. You are getting SiO2 in large quantities, CaO, Al2O3, and Fe2O3. So as far as the C&D waste is concerned, it can be sent to the building materials waste processing unit, which is shown here. And as far as the plastics and textiles are concerned, they can be sent to the waste to energy plant. But that still leaves us with about 80% material, which is soil-like. So really the problem is not taking out the C&D waste and plastics and textiles from but to see what do we do with the 80% material. And it is very attractive to say, can we use it in earthworks as a replacement for local soil? Or can we use it as compost in horticulture and agriculture? So the immediate question which comes to our mind is that, are there contaminants in it? And what are the engineering properties? So the first question we'd like to address is the soil-like material hazardous? And if you do the TCLP test, and these are the results of the previous studies, and these are the results. Let me see if I can use the pointer better. These are the results of our current studies. Then it shows that almost all the heavy metals which come out are below the TCLP limits. So therefore, the statement which comes out in all the tests that is being done is that soil-like material is not hazardous. These mountains have 77% of soil-like material. Where has it come from? It has come in with the municipal solid waste, but quite clearly the silica matrix or the quartz matrix is coming in from the local soil. So is the soil-like material similar to the local soil? That was our next attempt. And what we find is that the soil-like material from these old waste dumps, which are 10 to 20 years old, the organic content is now 6 to 18%, but still substantial. So we would like to recognize that when the MSW is put in these landfills, it probably has about 35 to 45% organic content and a lot more construction and demolition debris and soil, etc. When you compare it with the local soil, when I am using local soil for Delhi, we are looking at Delhi silt and Yamuna sand. The organic content is 1 to 1.2. And if I want to use this material for the purpose of earth fills, the regulatory limits are mostly that organic content should be between 1 to 5% at max. The other major difference is that the total soluble solids in the soil-like materials are very high. So I just want people to get an idea. This is 1.4 to 2%. The local soil has very little soluble solids, and these are primarily sulfates and chlorides. And there are some standards in Germany which says whether materials can be used without any restrictions or if they have to be used with sealing. So our chlorides and sulfates prevent unrestricted use of this material. And if you pass water through the soil-like material, and I would like to show you, this is silt, and we have a transparent water, the silt is settled down. But if you pass water through all the 3 landfill materials, you will get this kind of water. So it releases color. And it is not that with one washing, the color goes away. If I wash the soil 10 times with 10 times the volume, the color still comes out. And if I look at total heavy metals, though the material is not classified as hazardous as per TCLP procedures, chromium is elevated, 89 versus 10. Copper is elevated, nickel is elevated, lead is elevated. So really, while it's not hazardous, the heavy metals, both the total heavy metals, which means we digest the entire solid matrix, as well as the leachable heavy metals, which is in water, are high. So soil-like material is not similar to local soil either. It has higher organic content, higher total heavy metals and leachable heavy metals, very high soluble salts, and of course, leachable color. Then is soil similar to compost? Because many people say that maybe we are looking at it wrongly. It has got high organic content, and from municipal solid waste by aerobic composting, we get compost, and this is an anaerobic process, so maybe we can get compost. The only problem is that if the composting is done of mixed waste, you do get metals in it. So we try to see this as well. And we find that the soil-like material, these are the compost standards of India. How much organic carbon, total nitrogen, total phosphorus, and total potassium should be there. And we find that organic carbon is a little low. NPK is about all right. But when we compare the compost standards as per our solid waste management rules on heavy metals, we again have the same problem. Chromium shows up, copper, lead, even mercury and nickel are showing up higher than what is prescribed. So SLM is not similar to compost. It has lower organic content and higher total heavy metals in comparison to compost. So this is an important slide. Soil-like material is not hazardous, so everybody is calling it inert. But the soil-like material is not similar to local soil. Soil-like material is not similar to compost. It is being erroneously labeled as inert. Now, soil-like material is not inert, but can be classified as non-hazardous material, which is what we call municipal solid waste, from which contaminants do come out. And the soil-like material does not meet international guidelines. We have no national guidelines for this, for direct application or unrestricted use on land as earthfill or as compost. This is what we are finding. Are the engineering properties of soil-like material okay? Well, if you look at the C-, these are the previous studies. And if you look at the compressibilities and the permeabilities, these are the broad observations. The material has reasonable shear strength, but the shear strength can be low if the organic content is very high. That is the study, I think, of an earlier group of Song et al., which showed pretty low phi dash values. But in our material, that was not so. It has low permeability. And because of its organic content, it is expected to have time-dependent long-term settlements. So having looked at the soil-like material, we now start to look at bottom ash. Now, and we have to understand what is happening. Everybody is sending the municipal solid waste to these waste-to-energy plants. And if you send in 2,000 tons into the waste-to-energy plant, this is the Bhavana plant. And if you look at the mass balance, let's not go into the processing. Some material goes for composting, some goes to RDF and the waste-to-energy plant. We get about 570 tons of material outside of the plant. So that's going back to the landfills. So while we are reducing the amount of waste which is coming, we are still getting this waste to energy ash. And it looks like a perfectly nicely burnt material. And we looked at the reported, can we reuse this in earthfills? That's a bulk reuse. So there are enough evidence of this having been used in embankments or structural fills beneath the roads. So is there something to be bothered about? So this is the bottom ash from the Okla waste-to-energy plant. This is the bottom ash from the Bhavana plant. And these are all going back to the landfill. So this is a truck full of the ash coming to a landfill from which we have taken samples. We did exactly the same thing with the waste-to-energy plant. waste, as we did with the soil-like material. We've segregated it on site manually, and we found all these fractions. Now, again, you will see a soil-like fraction, and you'll see the CND and the slag and the stones. And if you really want to see how much is the soil-like fraction, in this case, it is from the Delhi plants, it's about 58 to 63%, and this is about 21 to 23%. And really what we are talking about is that how can we use this? The CND fraction can go to the building materials plant. But what do we do about the soil-like fraction, which is about 50, 60, 70%? And again, we are looking at the bottom ash has the same minerals, quartz, calcite, feldspars, and others. And it has same SiO2, 50 to 57%, CaO, 12 to 15, alumina oxide, 8 to 11, and ferrous oxide at 5 to 7. So the first question, is bottom ash hazardous? We do the TCLP test, and so there is some feeling that when you burn the municipal solid waste and and it's a mixed burn, it's not a sorted burn. So if it's a mixed burn, that all the heavy metals will sort of get some of them will go into the gaseous state and come back as leachable heavy metals, and it's deposited on the solid matrix. But there is no major accumulation of the heavy metals in the bottom ash. So we did not find there is accumulation in the fly ash, and those results we are not presenting here. That's the finer fraction, but there is no significant accumulation of the metals in the bottom ash. So bottom ash is not hazardous. So that's very good for us. So we can reuse it. And since it has gone through a process of incineration, one would expect that all the organics have burnt out because the temperatures in the furnaces are very high. So the question is bottom ash similar to local soil? And I would like to go back to the grain size distribution slide here. I don't know whether I missed it. No. So please note that bottom ash is predominantly sand size. So that's good material for us. And so it's not hazardous. Can we use it? Is it similar to local soil? Can I use it like sand? And here is what we get. Firstly, the organic content. So for whatever reasons, because we are doing mass burn and our waste is not well segregated, so there are lumps of soil also which go into the furnaces. So when there are lumps of soil, and if you're having a low residence time, you can have situations where all organics will not burn out. So you're getting high organics, very high total soluble salts, very high. And against chlorides and sulfates that dominate. The color is gone. The organic contents are lower than what we had in the SLM. SLM was 6 to 18%, but they're still higher than 5%. And again, there are elevated heavy metals. Just look at chromium in Delhi silt and Yamuna sand, and what we are getting here. Look at lead. And again, look at the leachable metals. And so bottom ash is not similar to local soil. It has high organic content, total heavy metals and leachable heavy metals, very high soluble salts in comparison to local soils. And another characteristic which I did not highlight is that its pH is also in the higher range, which sometimes affects the use of polyester geosynthetics. So what about the engineering properties of bottom ash? Now, these are good. You can get a very good shear strength parameters, you get low compressibility parameters, and you get a medium range permeability. So it's like good shear strength, low compressibility, and mid-range permeability. So now let's look at these two materials that we have. The ones which is the soil-like material emerging from the landfills, which is a residue, and one which is, so the soil-like material from the landfills is something which has come out from a bioreactor, an anaerobic bioreactor lying there for 10 to 25 years. And the waste-to-energy ash is something which has come out from a thermal treatment, which is instantaneous. It just goes in and gets burnt and comes out. So the questions we are saying is, can we have unrestricted use? Or do we reuse it with sealing layers and isolating layers? Or do we reuse it with sealing layers, isolating layers, and even a leachate management system? Or the other option is to go in for treatment. Now, various kinds of treatments are under development: blending, immobilization, size segregation, washing, carbonation, biological stabilization, and biocementation. These are under development, and we will not say much about this yet, but yes, for specific cases, these are applicable. And where can we use it in bulk reuse? So large area surface application for revegetation reconditioning or ecoforestry. So if you have degraded land and we want to do ecoforestry or we want to make it green, then the soil-like material appears to be very nice. Similarly, can we use it for earth fills, for raising low-lying areas or for landscaping? In Delhi, there are many deep pits, deep mining pits, which are 20, 30 meters deep. Can we close those pits? And finally, can we use it in embankments for road, railways, and water retaining structures as a structural fill? And in the end, can we use it for the structural backfill for the mechanical stabilized earth walls? So our findings suggest the following. Firstly, no unrestricted use. Secondly, if you are going to use it for revegetation and ecoforestry, you can use the soil-like material, but remember it has got elevated heavy metals and it can be blended with the topsoil, and we are only going to use a thin layer of this material. When we do revegetation, we are not putting a few meters of soil or tens. We are just putting a very thin layer, less than of about 50 centimeters or that amount. So if we blend it with the topsoil, we are able to bring down certain of the contaminants and we can use it because it has organic carbon and it does support vegetation. For earth fills, for raising low-lying areas or for landscaping, we think both SLM and BA can be used if they are non-structural earth fills because SLM is going to undergo long-term settlements, but with sealing layers. For deep earth fills, like in this 20, 30 meter deep pits, we can use this, but then leachate management, because this material, then SLM is almost like the municipal solid waste. It is giving out so many things. So we will have to recover the leachate, otherwise it will go down to the groundwater resources. For embankments for roads, railways, and water retaining structures, bottom ash can be used, not soil-like material. It has got too much organic content, but bottom ash requires sealing layers because too much salt in it, and we have to handle the leachate coming out. And for structural fills, we may use bottom ash if we can treat it by aeration to reduce the pH. So concluding remarks and the level of contaminants, heavy metals in municipal solid waste residues are not enough to classify them as hazardous. So people are calling this inert, but that's wrong. They exist at elevated levels. And I want to give you this simile, which I say very often. We've spoiled the waterways of Delhi. Yamuna is invariably dirty. We cannot clean it up. We spoiled our air. We are now getting smog every winter, no matter what we do. The only thing we have to be cautious about is we don't spoil our soil. And we can if we indiscriminately start calling material inert. So unrestricted use is not recommended. Restricted use in the form of sealing layers as well as for very deep applications of leachate is recommended. And treatment methods can be tried on case-to-case basis. So from here, we have to go here. And from here, we have to go here. And remember, when we are in a deep pit, we have to remove the leachate. Otherwise, you will get the colored water going into your groundwater resources. And as compost, as I said, you can blend it with the topsoil and use it for growing vegetation. And our experiment at the Okla landfill does show that vegetation grows well. But that does not mean, and it has to be non-edible vegetation when you grow on it. And these are the field operations going on in Delhi for the purpose of these are the three fractions, 1, 2, and 3. This is a soil-like material. It looks very voluminous, but remember, this is about 1/6 or 1/10 of these two fractions. And this is the process. 10 trommels processing 2,000 tons per day will take 15 years to make one dump come down. But what am I worried about? There's a recent NGT order which has directed that all MSW dumps be mined. And this is leading to unrestricted spreading and earth filling. When we tell somebody that, look, this material is not to be used, they say, no, it's not hazardous. We are doing the TCRP test, and which is correct. By undertaking large-scale unrestricted reuse of SLM, slow spreading of the contamination is taking place. Nobody's putting any sealing layers. So in 10 to 15 years, the dumps may disappear. But what's going to happen? If this dump goes into this deep pit, and this deep pit is not designed to remove any of the contaminants, all that we are doing is the old plume will remain, and we will create a new plume. So we have only studied a few contaminants. We are not chemistries or biochemists. We have not done persistent organic compounds. We have not done pesticides. We have not looked into this material in great detail. We did some very basic study, but old municipal solid waste is so heterogeneous because earlier there were no industrial waste landfills. So the industrial waste also used to come into this. So we have to be very cautious about how we spread this. So I'd like to just thank my colleagues in the Geoenvironment group at IIT Delhi, Professor Ramana, Yothiraman, and Wangla, who've been working with me on this. The work which I presented here is of Mohit Somani and Garima Gupta. Mohit Somani works on soil-like material, Garima works on waste to energy. Apurva is working on C&D plants, and Ali was working on coal ash. We've received some funding from the Ministry of Environment and Forests and IIT Delhi, which we acknowledge, and there's a core group of experts of any RCS with whom we for discussions from time to time. I'm grateful to them. And with that, I come to the end of my presentation.